India having to develop its own models. If tomorrow one of you guys get like $1 billion, how do you go about it, right? What are we training on? That is the most important question. To train a 405 billion parameter dense model, Meta had trained it over 16,000 H100s or something. The companies don't tell you. This entire exercise is called scaling, and that is pretty hard to crack. Hey guys, thank you so much for coming and joining me today. So as Paras mentioned, my name is Dwarak. I work on the pre-training team at Cohere. More generally, I also lead the training performance engineering efforts at Cohere. So we work quite a bit with distributed training, optimizing, large scale GPU clusters, trying to get these models really, make sure that we don't waste our GPU hours basically. So that's what I work on, and also kind of like a hardware aligned architectural design, and try to sort of tweak the model's architecture in a nice way. So today I'll be talking a little bit about pre-training LLMs. The way I thought about this talk is to maybe do 20 minutes of it, 25 minutes, and then open the floor for questions and interactions, so you guys can get in all your pre-training related questions as well. So I think the broad points that I wanted to cover is basically how do you go about begin to pre-train. There's a lot of chat about India having to develop its own models these days. So I thought, okay, if tomorrow one of you guys get like $1 billion and someone says, just go make the best model that you can, how do you go about it, right? So these are the most important bits in pre-training LLMs. The number one is data. Kind of sounds obvious, but what are we training on? That is the most important question. And the second is scaling. So what are we training, right? So it's when you look at these different model sizes that are coming out of these companies, right? Like Meta has a LLaMA 405B, 405 I think it is, LLaMA 3 405B dense, and Cohere has 111B dense model. You might think, how do they actually get to this size? Like, who decides if it's 405 or 300 or whatever, right? So that is basically the outcome of what we call scaling. It's another pillar in the pre-training pillars. The third is performance engineering. So how do we train these models, right? Like, to train a 405 billion parameter dense model, you need extreme amount of compute resources. I think Meta had trained it over 16,000 H100s or something, which is kind of insane. But you got to keep there are two questions here. There is the infra bit. You got to keep the infra really well supported. The GPUs must not fail too much. There should be not a lot of downtime in the hardware. And also the performance engineering, which is the modeling bit. How do you change your architecture such that it uses the GPUs really well? Like, one of the reasons why the transformer architecture is so powerful is because it's so it's so easy to train on, kind of, right, compared to RNNs, and that's why it sort of lend itself to scaling, as we know. So, and also, is there a lot of clever ways you can do performance engineering, like fuse kernels, very clever distributed routing, distributed learning algorithms. These are things that really help you, push your hardware to the limit. And the fourth, last but definitely not the least, is evaluations. How do you know that your model is really good? How did we train, right? Is it a good model, or is it just only good on the surface? Does it have any depth? How does it do when you push the model to its limits? That's where evaluations come in. That's also the area in which I'm the weakest. So I'm gonna not spend too much time there, but I want to make sure that you all understand that evaluations is super important as well. My forte is kind of in the performance engineering bit, so I have quite a few things that I can share with you there. But yeah. So pre-training data is the biggest delta between frontier and non-frontier models. I think this point is super important to internalize, right? Like, pre-training data might be the single most important thing that companies don't tell you, because we have quite a few open weight releases these days. Including ours, right? But the secret sauce is mostly in the data, right? So it's extremely important to get the data right, and the sort of trend has been such that the data scaling bit is really taking off, or rather it has really taken off. If you remember, GPT-3 model from OpenAI was trained on approximately 300 billion tokens, right? But now you see, this is a snapshot from the Quen 2.5 tech report that I took. So it's from 3 trillion tokens to 7 to 18 trillion tokens. That's a huge delta, right? That's basically doubling, or rather it's an exponential increase on the amount of data that you train on. LLaMA 3 was trained on 15 trillion tokens. So pre-training data is extremely important to get right, because that's where the model is picking up most of its knowledge, most of its abilities, right? Yeah. So if you think about data, we've all heard these statements that LLMs are trained on the entirety of the internet. But what does it really mean, right? Like, do we actually train on the entire internet? Well, what we actually do is take this thing called common crawl dumps, right? Common crawl is the service which crawls the entire internet and then they dump it. So, and this is not a single dump, right? Like, they do it once every month, if I'm correct, right? So you have every month common crawl dump. So, but you don't want to train on the entire dump. You want very powerful, sophisticated data filtering algorithms, because most of the data that you see is you kind of not really good. You don't want to train on it. You want to train on the high quality, sort of unique data that the internet can offer you. So, data quality filtering at scale is super important to get high quality pre-training data. So, human or LLM-based filtering. So, the Quint 2.5, if you read the report, one of the biggest delta that they talk about between Qwen 2 and Qwen 2.5 is how they use the Qwen 2 models to do data filtering for the Qwen 2.5. So this has a nice kind of flywheel effect where you use the current generation models to filter data and to sort of create data for the next generation models. So this is a sort of a self-improvement loop kind of thing, right? And this happens everywhere. But LLM pure is filtering. Yeah. Question, should we give it? Yeah, sure. Go ahead. Yeah. So I think that's a tough question to answer, really, because we don't really know where the boundary is, where it's okay to the model to where it actually hurts the model. Like, for example, if you, let's say, naively scrape GitHub, you might, and you just train a model on it, you're very likely to see huge loss spikes during the training of the model. That's because GitHub has a lot of, 256, it has a lot of whatever, some very, very, how do I say it, very weird tokens that don't really occur in real world. So it's not like free flowing language as such. It has a very lot of weird artifacts in there. And if you train on them, there is no probability distribution there that the model can actually model, right? So the loss just like bumps out and your training becomes a lot of very unstable and everything, right? So an interesting fact is, like, sometimes there might be huge number of repeated numbers that will just throw the model off balance, right? So it is true that some amount of data won't hurt you, but there are levels to it. Like, pure hex data sets are pure garbage. You don't want them in your training data. But if it doesn't like actively help your metrics, you can still have it in there because the model might pick up something that you don't really look at. And I think that is very related to the last point, is optimizing data mixtures, and I'll tell you exactly why, right? No, so 100%. That's a great point, right? And that's the second point. The second point is high quality reasoning, math, and code data improves the model's overall abilities, but it improves the reasoning and code abilities, like, to a larger extent. But what exactly is high quality code, math, and reasoning data? Where do you get it, right? Now, if you think about it, code and math, we know for sure that we can find it. So you can scrape it on the internet, or maybe you can do some semantic searching to get similar data to a few hand labeled gold samples. So this is definitely possible. But reasoning is not so obvious, because reasoning comes in different flavors. If you think about it, a text-based RPG, consider a text-based RPG. There is a world with predetermined set of rules, and you know that you have to adhere to these rules. And if you have a gameplay, right, like somebody is playing this text-based RPG, now that's a big trove of reasoning data, because a person is reasoning through what move to make, or rather what action to take in an RPG game, right? So there are different set of reasoning data available. You need to have an eye for it in a way. Like, you need to think of different novel ideas in which you can extract the reasoning information and make it available to your model so you can train on it. I think that is the second point. And the third is, of course, synthetic data, right? Synthetic data is super important now. So if you can't really find the data that you want anywhere, where you want to inject a certain ability into your model, the next best thing that you can do is generate it. So it's also not obvious to do that, because you need verifiers to do this at scale. Like, code, sure, you can do it. I mean, we've all seen like research that does this by using verifiers, compilers, and all these things. You can do it. But how do you do it for other things? How do you do it for spatial reasonings? How do you do it for like these different things? I think that's where the like a lot of researchers, a lot of alpha is in there. I think that's what we should be looking at. And so synthetic data for targeted attacks, specifically for the abilities that you want. And the fourth is optimizing data mixtures. This is kind of 50-50. It's partially data and partially scaling, and I'll tell you why. And it's also one of the most expensive processes in training. And I think there was quite a bit of discussion on DeepSeeks we use $5 million to train our model in the paper, right? And I think they were, to their credit, I think they didn't really overpromise. They told exactly what they told, right? It takes us $5 million to pre-train this particular LLM on such and such number of tokens. But I think people were like, oh, it just takes $5 million. We should immediately do it. Well, not really. To train the bigger run, what we usually call the hero run, right? The hero run is your final sort of prod run, as you call it. To do that, you need an incredible amount of research that tells you what architecture to choose, how big the model should be, which is the scaling bit, and what is the most optimal data mix, right? Like, so let's say you have 90% of common crawl and just 10% of code or math or whatever. That might not necessarily be the optimal mix. You need to find the specific weights of different data sets that goes into your pre-training data, right? And this is a super expensive process. And there has been quite a bit of research that tries to do this with reinforcement learning, with Bayesian optimization or whatever. And you can even do some correlation analysis to see if the abilities of your models are, how the data sets are related to that. But that's, again, a whole breadth of research area. Yes, 100%. Yeah, that's where the scaling bit comes in. So the scaling bit is like, how can you do all these experiments on a smaller scale and reliably extrapolate the learnings to the hero run? And yeah, 100%. Yeah. There's no way you can, I mean, at least based on my knowledge, there's no way you can predict everything about the hero run on a small scale, because there are certain things that only emerge at scale, right? Like, I mean, an 8 billion parameter model to 111 billion parameter model, there's just, the delta is so big, the model's capabilities are so big that you just can't predict it. In fact, one of my favorite anecdotes is sometimes the loss curves might be too stable at 8 billion, and you might run into nans or spikes at larger scale. And one of the reasons is maybe the bigger model is more sensitive to data, that the smaller model simply just, it didn't affect it. But the bigger you go, the more sensitive it becomes, because you have now more weights to sort of tune, right? So yeah, that's why scaling is so important. Yeah, I'm pretty sure it happens at every frontier lab, right? And there are definitely signs that you can look at. I think that's why in your training framework, it's very important to have the telemetry, or like the sort of bookkeeping, the logging as we call it. You need to log like different values. There's a lot of like theoretical reasons to why you should log these things. For example, gradient norms are directly correlated with training loss spikes. If you see a spike in gradient norms, you might see a spike in training loss curves. And then there is the second moment of Adam and the first moment of Adam and things like that. And then maybe on the top of my head, these are the things that you can look at. But of course, there are definitely things about the model state, the parameters, the norms, and the gradient norms, and the optimizer state norms that you can look at that can give you a sense of where the problem is. Sometimes it can be a data problem. Maybe if you dump the batch of data and you look through the data manually, you can see like random spaces or random numbers. These things throw off the model's trajectory. But sometimes it can purely be an artifact of numerical instability, architecture. Like you might want to do some specific operations in floating point 32, softmaxes, layer norms, and all these things. These things add up to the numerical stability as well. So there's no clear answer to it. You just have to cover all of your bases and go ahead. Cool. So that's the data bit. And this last point neatly gets us into scaling. But I just want to, this is again an excerpt from the Quen 2.5 tech report. And they talk about a little bit of how they weigh different domain data to sort of get the expected behavior out of their model, right? Yeah, and one more thing before we go to scaling is capability-based data generation. I think I heard, I spoke to a few guys here, and you're working on long context reasoning and things like that. So if you think about it, long context data is not really, it doesn't really occur in the distribution, so to speak, right? Like if you think about it, how many people actually talk for more than 5 hours? Not a lot, right? There are only a specific set of use cases. So if you just take the natural sort of distribution that gives you long context data, you might be skewing towards a few very specific things like books or movies or whatever, right? So diversity is key in long context data, in my opinion. So you have to be very clever about generating different styles of long context data to improve your long context reasoning abilities. And the second is reasoning, of course, and this is pure like reasoning through different problems. there is a penchant to always tie reasoning towards math and code, but it need not necessarily be that. You can be reasoning on video game, or you can be reasoning on movie or something, a script writing, right? So let's say you're writing a script for a movie, you'll have to reason your way through why a character does something, unless you're Bollywood writers or whatever, right? But you get what I mean. So you have to reason through how the script is sort of going to predict how your characters are going to behave. So there are different diverse ideas that can go into generating reasoning data as well. And of course, multimodal. We love Indic languages and making models for Indic languages, but how does multilinguality play with reasoning, long context? So these three things can help each other, right? They're not separate things. They go hand in hand. Like you can, let's say you're creating video understanding model. The video data can actually be long context data because your model is forced to reason through a super long context, right? So capability based data generation is super important to build frontier LLMs as well. End goal, we want to create a pre-training corpus that gives us maximum returns per token. So you have to really understand what abilities you want out of your model, create a way to quantify them, and tailor your data distribution towards those abilities. And of course, we want huge data because scaling is the name of the game. I think that really depends on run to run. Like ideally, you would love unique tokens, but also I think there is this recent paper, not recent, like there was a paper where it says that you can see a data set nearly 4 times in 4 epochs before you sort of squeeze all the juice out of that particular data set. So there's no really like hard explanation there. I think we really have to figure this with experimentation, basically. Coming to scaling, ablations are small scale experiments that we do, Paras, to your point, to figure out behavior of models at a smaller scale and to reliably extrapolate these learnings to larger scale, right? Like, I mean, thinking about command A, it's a 111B dense model, right? You can't keep training 111B dense models to, test every single change to your data set or architecture. So how do you shrink that to a more compact experimental setup, do your training there, get reasonable hyperparameters, and then scale them towards the hero run and make sure that you get a reasonably good run towards the end, right? So there's a lot of research in there. One of my favorite techniques is MuP. It's Tensor Programs by Greg Yang, and now Greg Yang is at XAI. So MuP is something we use for command A training as well. MuP is sort of a way to initialize and scale the learning rate of a model such that the activations don't really blow up as you scale the width of the model. So let's say you have an 8 billion parameter model at a certain width, embedding dimension 4096 or whatever, right? Now, if you just scale the width, you're doing a very predictable scaling, right? So there is a certain theory and a certain sort of parameterization that you can do for both Adam and your model initialization such that the activation norm doesn't grow as you increase the width, which means you get predictability in how the activations are increasing, right? So that gives you very nice parallel curves in hyperparameter tuning. So if you tune your hyperparameters on a small scale, increase the width, then you can be reasonably sure that these hyperparameters will be most probably optimal for the bigger run as well. So that's one technique. So yeah, tensor programs, MuP in particular, mostly talks about width. Depth is not a solved problem yet. There has been some research recently which gives you a reasonable heuristics for scaling in the number of layers, but usually, at least for command A, what we did is we fixed the number of layers before, shrunk the width, did all our experimentation, and then we scaled up on the width. No, not yeah. I think it's just a personal choice, to be honest. So personally, I'm a big fan of lesser number of layers because it really reduces the KB cache and it's greater for serving. And so fatter models, which are sort of shallow, is good, I think. But of course, there is a boundary. You can't have like a 4-layer neural network or something, right? That's probably not going to work. But yeah, I think my personal opinion is so there has been research which talks about the correlation between depth and reasoning abilities, but I don't think so. I think it's okay as long as you're in a reasonable range. Case in point is DeepSeek. It has 64 layers, and Command A has 64 layers. 64 layers for a 700 billion MOE is kind of ridiculous if you think about it compared to 3 years ago. I think OpenAI's GPT-3 was 175 billion and had 96 layers. So I don't think I've seen enough evidence to correlate depth to reasoning abilities. So if you have the choice, make your model like have a lower number of layers because it's better for the KV cache. And the second is isoflop curves, which sort of predict a model's performance for a given flop budget. So I think instead of thinking about number of tokens, number of model size in billions of parameters, you should start thinking about it in terms of the number of flops that you're spending. So for a given data set, for X number of tokens, and for a given model, there is a certain formula that you can find in any of the scaling papers, Chinchilla, what have you, which gives you how many flops you're spending to do the training run. And different flop curves have different characteristics. So the Chinchilla law, where it says that instead of scaling just on the model axis, you can scale on the data axis with a smaller model, right? It kind of makes sense when you think about the flop budget. So you should always like try to think in terms of flop budget and make, if you look at LLaMA 3 paper, they talk about how they made the isoflop curves for different flop budgets, and then they extrapolated the hyperparameters that they got in the lower flop budget towards the flop budget that they have a budget for. Like for example, let's say I'm the CEO of XYZ company. I go to my chief scientist and I say, you have 3 months, you have X number of thousands of H100 GPUs, figure out the best model. Now the chief scientist will work backwards. So if I have X number of GPUs, X that is Y, that translates to Y GPU hours, and a few trillion tokens, my flop budget is 1e to the 26 or whatever, right? So based on this flop budget, I can figure out how much data I need, what should be my model size. So that's how they arrived at the 405B dense number. So they worked backwards using the scaling laws, and they arrived at, for a given flop budget, the most optimal size could be something around the 405B dense area. So that's how you use the flop curves that you derive at smaller scale, you extrapolate them, and you can sort of make informed decisions on how much data you should train for and what your model size should be given your this resource constraint, right? Hope that makes sense. So this entire exercise is called scaling, and that is pretty hard to crack, right? Because any change that you can make, you need to have like a strong theoretical understanding of how this is going to affect the future, or you can't really predict what's going to happen. So that predictability is super important. And yeah, so this is again an excerpt from the paper. They talk about the scaling laws helping determine key training parameters like batch size, learning rate. Basically, the scaling laws gives you an insight, or rather a heuristic, to figure out all the very important parameters that you need for your hero run. And yeah, so there is a rather standard law called the square root law or something for batch size scaling. OpenAI has a paper quite old where how batch size scales with respect to the model size and the data as well. But ultimately, my opinion is all of this is best done empirically. So do different flop budget experiments, extrapolate the ideal batch size. For batch size, my comment is try to maximize the batch size that you can do. There is something called a critical batch size for every model. So let's say you can't train on something like 1 billion tokens per batch, right? Simply not possible. Your model won't learn anything. So you'll have to stay in the reasonable limits. I think one example I can give you is LLaMA 2. On the top of my head, I can remember that LLaMA 2 was trained on 4 million global batch size, so 4 million tokens per mini batch. And DeepSeek V3 was trained with 64 million tokens per mini batch, right? So you see the scaling. So DeepSeek kind of like went all in on the batch size and they just scaled it. They ramped it up pretty high, right? So yeah, batch size is one thing that can really affect your throughput on how long it takes to train your model. And if you can do some fancy, optimizers or math that can help you scale up the batch size, it's really good for you because you're keeping your GPUs very busy. You don't want GPUs to be idling, right? So, and that brings us to performance engineering, which is, I would say, not just because I work on it, the single most important thing to get right to compete with frontier labs, right? So you don't have billions in funding, you have a few GPUs. Now, what do? Well, you be clever with how you use your GPUs. So instead of relying on out-of-the-box frameworks, you look into every single law and you see where the bottleneck is and try to resolve it, right? So there are 3 important pillars in performance engineering: compute, communications, and systems. Kind of might sound obvious if you think about it, but I would say probably not. So compute is how your GPU is doing the work. What is it computing, right? How quickly it's computing it. Comms is, we have long since departed the age where you can train a model on a single GPU. Now you need to do something called sharding, where you take a model, you shard it, you sort of chop it into pieces, place it into different GPUs, and then communicate the data between the GPUs to perform a single forward pass or a backward pass. Now, communications is, can you take the data to the GPU in as little time as possible, so your GPU is not waiting for data, right? So that's communications. And systems is the overall throughput of the system. So let's say your compute and communication is super fast, but it takes 10 minutes to just log your loss into weights and biases. It's no use, right? Your training run is going to be dead slow. So the systems bit is also super important. So checkpointing should be really fast. If your run fails, the restarting of the run should be really, really fast. Logging should be really fast. Everything around the training itself should be really fast. Most importantly, data processing should be really fast. You should give the data to your GPUs, such that the GPUs are not waiting for data. Training framework, again, one of the most important things. Goals, you should have high performance training framework, diverse hardware support, because you don't know what's the next hardware going to be. So your abstractions need to be airtight, such that you can easily swap in one GPU for another, and flexibility in modeling. You don't want if all of your researchers are figuring out low-level kernels, nobody is doing research, right? So there is a fine balance between doing performance engineering and letting the researchers do their job, which is actually the modeling bit, right? So you need flexibility in modeling. If someone wants to make an architectural change, you can't tell them that, hey, this is not supported in our loss training framework, right? So Cohere chose JAX XLA as a training framework, and there are a few reasons for it. We call our internal training framework as FAX, innovatively. So FAX relies on XLA's SPMD partitioning. SPMD partitioning is a single program, multiple data sort of partitioning of the XLA system, where you create a mesh of all the GPUs. So let's say you have 16 GPUs. Now, these GPUs need to be aware of every other GPUs. Otherwise, how will they communicate between each other, right? So JAX does something called mesh creation, where you create a 16 GPU mesh, and you can shape it into whatever shape you want. It can be 1 cross 16, 16 cross 1, 4 cross 4, 8 cross 2, whatever, right? And you can then name the axis of the different mesh. So if it is 4 cross 4, and I name them as DPFSDP, which means I'm allocating the first 4 GPUs to my data parallel axis, and I'm allocating the next 4 GPUs, which is across each row in the matrix, to the fully sharded data parallel axis. I have an image from Google's switch transformer paper that explains it quite clearly in the next slide, but yeah, the neat thing that JAX XLA gives is SPMD programming model makes it super easy to shard and reshard things. So you can write very complex sharding strategies like NVIDIA Megatron's tensor parallelism or pipeline parallelism pretty easily with XLA's SPMD, and that's why we chose it. Ease of resharding, so we chose XLA and we sort of tailored it for our use case, where we rewrote most of the sharding strategies to figure out what is the best way you can squeeze out most amount of juice from your GPUs. And of course, out-of-the-box support for techniques like mixed precision, activation remat. Activation rematerialization is a technique where in the backward pass, instead of storing the activations, you sort of rematerialize them to compute your gradients, right? Now, it's very important, because if you store your activations, you're eating into very precious GPU memory that you have available, right? Activation remat sort of helps reduce your memory footprint, and JAX gives that out of the box. So yeah, this is a neat image from the Google switch transformer paper. You can see different sort of sharding strategies here. You have data parallelism, model and data parallelism, different things, right? So the way I think about it is data parallel is purely parallel in terms of data, right? So every GPU has a copy of the model, and you get some data, some subset of the data as input. You do your forward pass, backward pass, and then you do one collective op called an all reduce to synchronize the gradients between the GPUs, and then you apply them in the optimizer state update. This is the sort of more basic form of parallelism. It's been around for a while. It's called DDP in PyTorch, I think. So data parallelism has been around for a while, and it's the easiest way to scale up. There's one problem with this, right? And that goes back to the critical batch size thing I said. So let's say you have 16 GPUs. If you use a batch size of 16, you'll get at least one sample per chip, per GPU, right? So your data parallelism works out great. Now let's say you want to train on 16,000 GPUs like LLaMA 3, 4 or 5 did, right? You can't have 16,000 as your batch size, because you're going way over your critical batch size. So what you have to do is you have to reshape the mesh, repurpose